In this graphical approach to the concept behind Riemann sums, we're going to look at the idea of using rectangles to estimate the area between a curve y equals f of x and the x-axis from x equals a to x equals b. Now we almost have a rectangle here. The two sides at x equals a, I'm using a equals 2 in this example, and x equals b, I'm using b equals 10, are vertical lines, so they're straight, they're parallel to each other, and they meet that x-axis at right angles. So we have three sides of a rectangle. The fourth side, however, is the curve, y equals f of x. So that's not straight, it's not perpendicular to the vertical sides, and it doesn't form a rectangle. We're going to form a rectangle by creating a horizontal top, and we're going to take the height of that top from something to do with the curve y equals f of x. Now, one thing we can do, which will give us an overestimate of the area, is to use the highest point on the curve between x equals 2 and x equals 10. That highest point has a height of about 5. So if we give our rectangle a height of 5, and of course it has a width of 8 because that's distance from 2 to 10, then we'll have an area of 40. And the area of that rectangle is obviously larger than the area of the shaded region under the curve. So we know the shaded region has area less than 40. How much less? We're not sure yet. Then we can do a similar thing, getting an underestimate by taking the height from the lowest point on the curve. The lowest point has a height of about 1. We multiply that by the width of 8. We get the green rectangle there that has an area of 8. And we can see that the shaded gray area is definitely larger than the green rectangle and smaller than the red. So it has an area somewhere between 8 and 40. Now, 8 to 40 is a pretty wide range. Imagine a friend of yours has found someone they think would be the perfect partner for you. They're trying to fix you up with this wonderful, perfect person that you haven't met yet, and you're asking a few questions. And you say, well, how old is this perfect partner? And your friend says, well, I'm not sure exactly, but somewhere between 8 and 40. You may feel you don't have enough information yet. So we have some other ways of choosing the heights of the rectangles that can give us some perhaps better information. One is to take the height from the value of the function at the left side. So our left side is at x equals 2. We put 2 into the function and we get a height of about 4. So we can use the height of the rectangle as 4. The width, of course, is still 8, and we get an area of 32. The left end is generally not the highest point or the lowest point. So this isn't going to give us something that we know is too large or something that we know is too small. We can just say the area is about 32, give or take something. We could do the same thing with the right side of the rectangle, generally not the highest or lowest point. It could be one of those, but frequently not. And we find that at the right end of the rectangle, the height is 2. And if we take that height of 2 times the width of 8, we get an area of 16. So we can say the area is about 16 or about 32-ish. The third thing that is commonly done is to take the height from the middle of the rectangle. So we need to know what's midway between 2 and 10. One way to get that is to average them. Add them together, divide by 2, and we find out the middle of the rectangle is at x equals 6. And at x equals 6, we find what the height of the curve is. It's about 3. And that gives us a rectangle with a height of 3 and a width of 8. And so that rectangle has an area of 24. None of these are guaranteed necessarily to be too high or too low. We just say they're somewhere in the right area. So the shaded area is greater than 8, less than 40, and sort of close to 32, 16, or 24. We still would like more information than that. One way we have of using rectangles to estimate the area and yet getting a more precise estimate, something closer to the true area than what we have so far, is to break our region up into multiple rectangles. Instead of modeling it as one large rectangle, we model it as 2 or more smaller rectangles. I'm going to model it here with 2 rectangles instead of 1, and so each rectangle is half as wide as the total region. You don't have to have your rectangles all of the same width as each other, but it keeps things simple, and it's what we're going to do here. And now I'm going to use the overestimate model, where we take the highest point in the region, but do it separately for the 2 rectangles. For rectangle number 1, the highest point has a height of 5, and we have a width of 4, so that's an area of 20. But for rectangle number 2, the highest point is lower. The highest point is at 3, and with a width of 4, that's an area of 12. So our overestimate is now 32. We can say the area is something less than 32 square units. We'll do the underestimate the same way. On the left, we find the lowest height is 3, and 3 times 4 gives an area of 12. And on the right, the lowest height is 1, and 1 times 4 gives an area of 4. So that's a total of 16. So now we can say that our region has an area something greater than 16 and less than 32. Summarizing our results so far, we can see that with one rectangle, the best we were able to get is that the area is less than 40 and greater than 8. But when we go to 2 rectangles, we're able to bring that overestimate down. Instead of saying it's less than 40, now we can say it's less than 32. At the same time, we're able to bring the underestimate up so that instead of saying it's greater than 8, we now can say it's greater than 16. So this region here on the number line that shows where our area is getting narrower. The left end is moving to the right end is moving to the left, and we're narrowing down on that place where the true area of the shaded region is. We can continue with the other methods of finding the heights using the left endpoint, the right endpoint, and the midpoint. These are often used because it's not difficult to tell what the value of x is at the left end of an interval, or the right, or the middle. It may be a good deal more difficult to tell where the function reaches its highest or lowest points. So we'll do that here, continuing with 2 rectangles. The left rectangle on its left end has a height of 4 and a width, of course, also of 4 and an area of 16. And the right rectangle on its left end has a height of 3, and that gives an area of 12. Looking at the right end, the left rectangle at its right end has a height of 3, and the right rectangle at its right end has a height of 2, so we get an area there of 20. And finally, taking the midpoints for each of the intervals, the left interval runs from 2 to 6, so the midpoint there is 4, and the height at 4 is approximately 5, so that gives us an area of 20. And the second rectangle has a midpoint at x equals 8. The height there is about 1, and that gives us an area of 4. So we get our left end, right end, and midpoint estimates as we did before, but they're all numerically closer to each other than they were the last time. Using 2 integrals brings all the different estimates toward each other and also toward the true area of the shaded region. We could do even better with 4 rectangles. So here we subdivide our region into 4 rectangles of equal widths. I'm numbering them 1, 2, 3, and 4. And we look at the high points of each of those. Now the first 2 rectangles have pretty close to the same high point. I'm rounding this off a little bit. I want something we can see from the graph, so it's not terribly precise, but they both have heights of about 5. For the third rectangle, the highest point is on the left end, and it's about 3. So the area of that rectangle is 6. And for the fourth rectangle, the area of the highest point is on the right. It's 2, so the area of that rectangle is 4. And that brings our overestimate to 30. We can do the same thing finding the low points from each of the intervals. On the first one, the low point on the left is a height of about 4. On the second one, the low point's on the right with a height of about 3. And the third and fourth ones, the low point is approximately 1. So that gives us an area of 18 as our underestimate. Then we can carry on to do the left end, right end, and midpoint estimates as we did before. So the first interval has a height of 4 at the left end, the second has a height of 5, the third one 3, and the fourth one 1. So using the left end, our total comes out to 26. On the right ends of the intervals, we have a height of 5 for the first one, 3 for the second, 1 for the third, and 2 for the fourth, giving us a right end estimate of 22. And finally, for the midpoints, we have to find the middle of each of the intervals. The first interval goes from x equals 2 to x equals 4, so the middle is 3. And we find the height of the function at an x of 3, it's about 5. And then we do that for the second one. The middle is at x equals 5, and the height's about 4. The third one, the middle is at x equals 7, and the height's about 2. And the last one, the middle of the interval is at x equals 9 and the height's about 1. And that makes our midpoint estimate a total of 24. To summarize all of our results, we found areas using the highest point on each interval, the lowest point, the left end, the right end, and the midpoint. And we did that for 1 rectangle, 2 rectangles, and 4 rectangles. As we get more rectangles, the highest point steadily comes down from 40 to 32 to 30. And that's a number that we can say is definitely greater than the area of the shaded region. The lowest one keeps coming up from 8 to 16 to 18. And that's something we can say is definitely less than the area of the shaded region. The left end, right end, and midpoint estimates are not guaranteed to be too high or too low. They could be either of those, or they could be exactly correct. But you can see that they're getting closer to each other. With 1 rectangle, we had a spread of 16 to 32 on those 3 estimates. And by the time we're at 4 rectangles, the spread is only 22 to 26. So it's much narrower. The midpoint estimate has stayed exactly the same in all of these. That's a coincidence of the particular problem we're doing. The midpoint estimate does not always stay the same as you increase the number of rectangles. That just happened in this problem. And the midpoint estimate turned out to be between the left end estimate and the right end estimate. And again, that happened on this problem. It's not guaranteed to happen on all problems. Now we're going to take a closer look at how making the rectangles narrower gets us more accurate results. On this page, I'm going to use the heights of my rectangles always from the right end of the rectangle. We could do something very similar with the left end or the midpoint, but I'm going to use the right end here. So look at region 2. If we do region 2 with just 1 rectangle, then we have a height of our rectangle is 3, the width is 2, the area is 6, and that's certainly part of the gray area that we want, but we're leaving out quite a bit of that gray area on the top. So now I break the region into 2 rectangles, each half as wide as the rectangle we started with, and now we have 2 different right ends. Each rectangle has its own right end and therefore has its own height. And we see the one on the right has the same right end as before and the same height, but the one on the left has a right end that's now higher. It's now at 4, and so we're taking in more area, more of the shaded gray area that we actually wanted to find. So we're getting a more accurate result. Now, if we look at region 4, a similar thing happens in reverse. If we take it as 1 wide rectangle, we have a height of 2, width of 2, area is 4, and we're taking in all of the shaded gray area that we want, but also quite a bit of white area here that we don't really want. So if we break that down into 2 rectangles, the one on the right has the same right end as before and the same height, which is 2, but the one on the left has a lower height, and so we're taking in less area, less of the area we do not want. So when the rectangles become narrower, the heights of the rectangles are able to better follow our curve, and we get more of the area we do want, less of the area we do not want, and generally speaking, a more precise estimate of how much area is under that curve. Finally, I would like to look at an animation that I found on Wikipedia. This animates Riemann sums, always taking their heights from the right ends of the rectangles, which is why it's named right box. It was created by a Wikipedia content provider named 09 Glasgow 09, and this page gives the information crediting him for that work. You see, as he adds more and more rectangles to this region, and each rectangle becomes narrower and narrower, the heights of the rectangles are following the curve more precisely, and the area of the rectangles is more precisely matching the area under the curve. Now, when we calculate these by hand, as I've done in this video, 4 is enough to get the idea. But if you're using this as a calculation method assisted by a computer, you might break your region not into 4 rectangles, but 4 million rectangles, and you can get very precise estimates of areas. As long as you're using a finite number of rectangles, it is an estimate, it is not the true area. But we can get estimates that are good to 10 decimal places or more, and at that point, really, the difference between the estimate and the true area is perhaps something that we don't really care that much about. This concludes our conceptual introduction to Riemann sums, In the next video, we will look at a more calculational approach using the formula for the curve.